Okay, now we're going to move into movement with vectors, and we're going to talk a little bit about what does speed mean, how do we use this stuff in practice. And this will kind of flow into some of the demos that we'll go and talk about for the assignment and things like that as well. So whoever made this lecture materials originally was really into Nicolas Cage, and I thought about like, maybe I should take that out and kind of, be just the facts. But I kind of like Nicolas Cage, so like let's do it. You know. So let's talk about speed. Not really sure why, but cool. So Einstein didn't necessarily say this first, but I get it. This speed is a rate of change of a position. So if you're talking about classical mechanics, right, your position, your displacement x is going to be equal to your original position x0 plus your velocity, which is the rate of change of your position times time, right? Or velocity or speed in this case, if you're just thinking about one dimension, is meters over seconds. So that's kind of the idea. In computers, right, you're kind of thinking about how many pixels is it moving or how many units, and you get to define what those units are. And I think that's really an important distinction between the real world and physics and video games, where in video games, like, you can represent the real world with meters and whatever, inches, but it's not really real, right? Like, they're kind of made up. It's sort of an abstraction. And so you can think about it as pixels even if you want. You don't even need to think about it as time. You can think about it as frames. There's a lot of ways to do that. So speed is actually a scalar. And it's really kind of the magnitude of your velocity, because it doesn't have a direction, whereas velocity does always have a direction, even if it's the same direction all the time. So to measure speed, what we do is we kind of take a look at the positions of a particular object over a number of times, and we can kind of figure out how fast is it moving per frame, right? In this case, we're moving about 3 units per frame. But what is it, right? Like, what kind of units are we? Are we talking about pixels? That's pretty slow, right? 3 pixels per frame, that's quite slow. Or if it's 3 unity units, as you know, 1 unit can be quite large, or in some cases the entire screen. That's probably very fast, right? 3 units per frame, you'll barely even see it for a frame. And so you can kind of think about to add speed to an object, you can either add to its x or subtract from its x, or add to its y and subtract from its y per frame, right? That's the speed can be independent, so like of axis. And this is sort of why we use vectors, but we'll kind of get into that, and we're going to kind of peel back. Imagine we don't know anything about vectors. Imagine I just want to make a ball move along the x-axis or the y-axis at a particular speed. And so every frame I'm going to add that value to it. So here's an example of this, right, where we have, we're still using vectors, but we're kind of hacking around it, right? You have your position, which is 0, and we define the speed, which is 0.1, and then we're adding every update, every frame, that speed. And then every update, we each set the position of our object to that position. And that gets us pretty far. So let's maybe do this. Probably should have had this up and running before. Let's create a new 2D object, 2D movement example. And then I can use this to get into some of the later things. Can't resolve template. What? Let's do a new one. 2D movement example. Great. Movement example. Come on, Unity. What? Okay. I'm going to pause this while I figure this out. Okay. Now creating a example project that will hopefully not suck. Okay. Great. So created a little new 2D thingy, which is good. Oops. I want that here. I want game down there. Okay. Great. Okay, so let's add a new little sprite. No. It's supposed to be transparent, yo. Is that just lying to me? Alright, fine. We'll create a new... We'll just use the tank example. It wasn't as exciting to do that. I wanted to do the, Pickle Rick, but unfair. So let me throw this into here. Let's create a new empty object, which we'll name tank. And then in our images, let's throw these three in here. No. No. Okay. Tank turret. Tank wheels. And then I guess the chassis goes down here. Fine. The turret we're gonna put at Z 1.1. Oh, right. I'm gonna put this at 0. Depth, and then the tank turret we'll put at 1, which is not. -1. Oh, I see. We're in the opposite direction. Great. Cool. So let's make the tank way smaller than this. Cool. Great. And let's make this into a prefab. And prefab. Let's delete this guy. And let's throw the tank into our scene. What's the deal though? I wanted to use my Pickle Rick guy. No? I guess it's not actually transparent. Bummer. All right, whatever. So, well, this is kind of fun actually. If you do this, you can kind of see the ordering, and that's maybe this is something important because if you're trying to do these sprite kind of compositions on your own, you might notice like, oh, why is it upside down? Why is it not working the way I expect? Well, you do have to sort of stack them so that from the perspective of the camera, one thing is in front and one thing in the back. But let's just move it for now. Okay, great. So it's here. I'm going to add to my prefab a script. New script, and we're going to call this vehicle. And open it up. So first let's go back to our thing. So assume that we start off with a vehicle position of 0. Let's start that. Let's start there. Let's do private for now. Vector 3. Let's go to vehicle position. All right. We can do that here actually. Vector 3, 0, 0, 0. You'll notice actually you can do it with only, oh, somebody asked me for this. Let's do that. Cool. All right, so now you can see where I'm pointing. Hopefully that's helpful. I know this was a request in the Discord, so yeah, hope that helps you guys see where I'm pointing. You'll notice that you can actually have different, you can have a 2D or a 3D set of functions for a vector, but I'm going to use the 3 just so that we don't forget. Great. Cool, I like how it shows everything that I'm doing down there, which is fun. Okay, so let's also define our speed. And let's call it 0.f. And then also we're going to, in our update function, right, set vehicle position dot x plus equals to speed. Great. And then finally, we want our set our transform position to our vehicle position. Great. So now let's see what happens. Whoa, it's off to the right. The reason that's happening, right, so we're taking this position, and once per frame, we're adding 0.1 to it. So you can see again, it starts off, it actually moves it to 0, and then it'll move it 0.1, 0.1, 0.1 each time. Great, so now we can kind of see how that works. But it doesn't really, it gets us there quickly, it makes movement happen very quickly, but how do we change one from the other? Right now we have the same speed for both the x and the y axis, and also how do we change the direction? Like, it's not quite enough for what we want. So let's kind of take a look at another way to do it. Yeah, I mean, I'm pretty sure this is something Nicolas Cage thinks about all the time. Right, and we should obviously use vectors. Okay, so let's jump into how to use vectors here. Like, we can use vectors for velocity, acceleration, we can use it for gravity, we can use it for the direction and heading. We can use it for like everything, really. You know, we can use it to make toast in the morning. We can use it to make a sandwich. Sometimes we can even use it to do our taxes. Vectors are really useful for everything. Anyway, so how do we do this? Instead of having a scalar value for speed, we're going to use a vector instead, and we're going to have that speed as a value inside of the vector, and then we can do it just that way alone. So let's apply those changes. Okay, so instead of speed, we are now going to use a vector speed, or let's just call it speed vector 3. I like how the bottom it's just going on and on, because that's actually valuable. And then we're going to go speed.x, speed.y. And let's see what happens here. Space doesn't do anything. Cool, same thing. And what's nice here too is if I make this less, let me make this slower. Now we can change the sort of trajectory a little bit. You'll notice that it's kind of now going in a slightly lesser y angle, which is cool. Great, so we've done that. But how do we change the direction? How do we add or subtract speed from each frame? So now we can kind of think about the direction that we have. So, wow, these are some deep fakes. Yeah, okay. Like the idea is basically you have a direction that represents which way you're looking, and then you can apply a velocity in that direction. And so let's kind of see how we might be able to do this, right? We can move in a magnitude, a particular magnitude is set as a speed, and we can then sort of apply that speed to the velocity as needed. Right, if we want to go left, if we want to go here, if we want to go positive on the x, then we do that. If we want to go negative, we subtract. Same thing for up and down, right? If we can now control it independently. And so, yeah, that's kind of it. I mean, I'm sorry I'm going through these last few slides, but we're kind of reiterating the same point ultimately that we're talking about throughout this lecture and the one before. And so if you know your direction and you know the speed, then you can apply, you can get a velocity out of that effectively, right? You multiply your direction by your velocity. And so imagine that your speed is 5 units. Continue. Okay. Imagine your velocity is 5 units per frame, and your direction is 1 on the x-axis, meaning you're looking straight down the x-axis. You would multiply 1, 0 by 5, and your resulting vector would be 5, 0. And so for that frame, you'd move 5 units on the x-axis. That's kind of the idea there. If the direction isn't normalized, then your velocity won't be correct. And this is kind of what we were talking about before. You really want your numbers, your velocity, your direction to be normalized, because now you can kind of separate your speed or magnitude from your velocity. If you multiply a velocity that isn't normalized by 1 by a speed, your actual speed is going to be sped up by the velocity. Now, like I was saying before, you can not do speed and you can just have a velocity vector and rotate that and apply it and kind of scale up and down the velocity vector in terms of magnitude. That's also something people do, but it's just more stuff to keep track of. It's actually easier to split them across. So if your velocity is a change of of your position over a set amount of time, then how do you how do you determine the velocity from a starting point to an ending point? And in this case, we just do a subtraction. We realize the difference between 8 and 2 is 6, and 4 and 2 is 2. And that's the way that you kind of understand how to kind of retroactively figure out what your velocity is. Right, it's kind of sort of like the slope of a line. Velocities can absolutely have negative values. So if you can imagine, I'm going down the x-axis at 5, like at a speed of 5. I can apply a negative speed of 1, and now I'm going 4. We saw this before, where we saw that if you have a velocity speed that you're applying, and then another velocity in the opposite direction, that's kind of like a subtraction. So you can subtract. This is actually used pretty often in things like drag or wind resistance and things like that. So yeah. The thing about velocity, so if you're familiar with the Newton's laws of motion, right? A body at rest will stay at rest. A body in motion will stay in motion, right? This is actually kind of like a big deal, and people figure this out, that if you have a thing and it's moving, it's going to keep moving, unless there's some other force being applied on it. And so, often your velocity is actually that thing. It's going to be applied every single frame, and so it's really kind of comes down to a speed with a direction. I know that I'm explaining this like 3-5 different ways and but you'll notice like when you actually do it, it's pretty straightforward, but it's kind of confusing to think in this direction, in this sort of mindset, right? Like velocity and acceleration and position are all different things, and also the speed and how do you do it. There's a lot of different things. So in this case, this particular object is moving 5 units per frame. And so the velocity from the starting point, 10 to 4, to the ending point, what would that be? That would be, again, a -4. You're going in the negative x direction, and 3 up in the y. And so this is kind of an important bit. This is actually when things start to get interesting, because you are now actually moving and changing how your object moves around. Changing a direction means change of velocity. You know what? I'm not a big fan of this thing here. I don't want to buy it. Here we go. Sorry. I'm going to get rid of it for now. Oops. So if you want your velocity to change, then the velocity has to change. And that way, that gives you direction changes as well. So to do that, we will have to rotate our object, or rotate our velocity, and that's when things get kind of interesting. But before I do that, let's jump into this code here. So what we were kind of talking about, well, the position is going to change with x and y, the velocity is going to change with x and y. So first let's make, let's kind of play with this idea here a little bit, and let's try to change our velocity as we change the input. So let's say input get key code, left arrow. We're going to set our speed to be equal to and then I'm going to be very verbose here. I'm only going to do this for the x-axis for now, is equal to negative. And for now, and let's set this to 0 and 0. So here what I'm doing is if I'm pushing the left arrow, the speed is going to be 0.1. And if I'm pushing the right arrow, the speed is going to be negative 0.1. Otherwise, it's going to be 0. So what will happen here? So first it's going to go to the 0 position. Then if I hit left, great. If I hit left, obviously I did something wrong. Left arrow. Speed.x equals. Okay, it should work, actually. I'm not sure why. Oh, because I don't know how to code, clearly. Okay, if I'm hitting left, it's going to be negative. If I'm hitting right, it's going to be positive. If I'm not hitting anything, it's going to be 0. Obviously, I've had enough coffee today. So left, great, right, great. You'll notice it's only happening when I'm hitting the keys. So that's fun. And now we can do the same thing for up and down. up, down, and now we can do that for y. And you notice the main reason this is working is this code here. We're changing the velocity based on the key input, but whether or not that is being used is only because at the end we're adding that velocity which is being changed. So right now I'm holding both. It's velocity that way, and so you can see already I'm getting a lot just from very limited code, like just a few lines of code setting this velocity. It's quite effective. Cool. Great. So now let's talk a little bit about rotation, because you can kind of imagine there's another way to do what I just did. Instead of, you know, having it this way, I can also create a float speed magnitude. And we're going to change it such that we're going to change this to velocity, which none of this is going to work now. Actually, I'm going to get rid of the left and right arrow. You'll see why in a minute. And then if I go up, I want to go faster. If I want to go down, I want to go slower. So speed, I'm going to add to it 0.1. Let me do this way. I'm going to change this name to speed up here. And I don't need this either, because I'm going -1,1. You'll see what I mean. Just a minute. And here we're going to change this to velocity. In fact, we don't even need x and y. We can just do velocity, because these are both vectors, right? And so now my speed is 0, my position is 0, my velocity is 0. And if I hit up, then I'm going to increase my speed. If I hit down, I'm going to decrease my speed. So I'm going to go hit 0. And watch, if I hit up arrow, not much happens. But if I keep on hitting it, nothing seems to happen. Great. Sorry. So what did I miss out? So speed right now is being changed, and the velocity is not being changed. We need to take velocity and multiply it by the speed. So now, when we start, now if I hit up, I'll start moving ever so slightly. Or not. I don't know what happened. Well, the velocity, you'll notice, is also 0. And so 0 times 0 is 0. Anything times 0 is still 0. So we have to choose a velocity orientation. So say we want it to move up. Now if I hit it, if I hit up, it will actually start moving ever so slightly. Hitting down, whoops, hitting down made it go faster for some reason, which is not really the intention. Let's try that again. So often I'll purposefully make mistakes to kind of show you guys some of the common mistakes that people make. In this case, that was not one of them. That should have been actually going slower. And the reason is unclear. So let's slow this down even further. You notice just how sensitive it was when we did that. But one thing we can do, by the way, is we don't need that else if anymore, because we're now in a place where we're manipulating the speed independently. So if I hit play, now if I hit up, we'll move up slowly. If I hit down, we really should be slowing down. We should be going the opposite direction. Oh, well, if you subtract a negative number, you add. Okay, great. So now if I hit play, this should work the way I'm intended. So now I can go faster. To slow down, I hit down, or up, or down. You'll notice that there's a sort of momentum to this now. If I'm hitting down, I'm going to keep going even without touching the keys. If I hit up, we keep going. So like, this is going to start looking more and more like the behavior that you expect from your own, from the assignment that you have kind of lined up. All right, let's move on to rotation, because now I can only move in one direction. Obviously, I can change this velocity vector. I can start to point it, but how do I change that? How do I start to, manipulate that? There's one easy way, which you can kind of imagine. I can like add x and y to it, but it's not really what we want. What we want to do is we want to start to rotate the velocity. And how do we rotate that? Well, we're going to use this terrific thing called a quaternion. Now, quaternions are complicated. They are effectively a set of mathematics that Hamilton discovered, effectively how to do complex numbers in 3 dimensions. If you're interested in this, I really recommend reading up on the math. It goes quite deep and they're really interesting. However, for the purposes of this lecture and for this class, just think of quaternions as an orientation in space in a way that Euler angles like x, y, z can't necessarily cover. What Euler angles really have a problem with is what's called gimbal lock. And gimbal lock, if you can imagine a gimbal, like a film gimbal, you can rotate up a camera, but what happens when it's looking straight up? The math, it kind of gets locked. You get to this point where you can no longer rotate. You get stuck up there because you've rotated, and now any mathematical operation won't let you get out of that situation unless you look down. And if you played a first-person shooter, you've probably experienced this a little bit, where you look up and it stops you from looking behind yourself and being upside down and all this stuff. And so, we need to kind of have a way to prevent that from happening, and quaternions actually allow you to do a much better job of rotating in 3-dimensional space. So the way we use rotations is in Unity is using quaternions. We did this in the clock exercise already. We figured out the rotation by using a quaternion from the Euler angles given to us by the deflection of the position of the mouse. And so to do this, it's actually pretty simple. You just create a rotation, and then you apply it to the transformation like we were doing with a position. So let's do that. For example, let's do private quaternion, or call it our orientation equals new quaternion. We want to use the Euler family. You can make a quaternion out of the x, y, and z values and then the w, but those values aren't like x, y, and z Euler angles. It's a common mistake people make with quaternions. That's not necessarily true. Actually, the way that a quaternion kind of works is it's almost like there's a vector, and it's a rotation about the vector in space. And the x, y, z is that vector. So it's kind of like, what does that even mean? Like, it's like there's a vector and a rotation about that vector. So how do you get to your resulting orientation? It's not actually the most convenient way to think about it. So better to use something like the Euler angles, which will allow you to provide an x, y, and z rotation. And in this case, let's do this. We're going to need a new quaternion, Euler, and then we're going to do 0, 0, 0, 0, 0, 0. Let's rotate us about the y-axis by 15 degrees. And And you'll hopefully notice that when we run this, our object is rotated by some amount. No? Okay. Well, what we need to do is we need to set our transform.rotation to the orientation. And now, when we apply that, it should rotate. Unfortunately, though, we did a bad thing, and we rotated by the y, and y is up. And if you rotate about the y, then you rotate like into the screen. We don't want that. Actually, we're rotating about the z. The z is what we're looking into, and so that's the rotation axis that you're gonna really be dealing with most often in the 2D version of this. And you can see now it's rotated ajar. And you'll kind of notice, so let's set it to 0 for now, and now we kind of understand how we can create a rotation using a quaternion. And so how do we change the direction of our object? Well, what we can do is we can multiply the rotate, like we can use a rotation to rotate a vector. And that's kind of a bit of a it's a lot of math. Like it's a very straightforward thing for quaternions to do to rotate a vector. It's one of the things that they're best at is taking a vector and changing its rotation. And you can kind of see in Unity, it's as simple as taking a quaternion and multiplying a vector by it, and it'll automatically do all the math for you. This isn't the same. I want to really make clear, this isn't the same as a dot product or a cross product like vectors. Even though a quaternion has an x, y, z, and a w, it's like a 4-dimensional vector. It's not the same thing. There is math specific to making this work that is quaternion mathematics that allows this to work. But what's really nice is you can just create a vector. You can create a rotation. So if I wanted to say, okay, I want to rotate a particular vector by something, then I just multiply it. So let's kind of take that into here, where we can do the following. Let's set our velocity to 0, and then let's create a new vector, 3v, let's call this the heading vector. And as we saw in Unity, our tank is pointing up, and so our velocity, our heading vector right now is looking straight up. We have a orientation, a quaternion here. And for the time being, we're actually not going to use this at all, but let's leave that code there. And then our orientation is going to, our rotation, we're not going to set the rotation here for the time being. Actually, let's take that out. And so what we can do now with the left arrow, we can create a new quaternion Euler angle. Rotation, and we're going to create it as 0, 0. Left is going to be into the counterclockwise, so we're going to make -1 degree. Sorry, I need to create quaternion. And then we're going to do the same thing here. We do positive, and then we take our heading, and our new heading is going to be equal to heading, our rotation angle times the heading. Just like that. And nothing here. And then what we're going to do is our velocity is going to equal our speed times our heading. And that's it. And so what's going on here? Let's see what happens. So now if I hit up, I'm going to move up and down just like we did before. But you'll notice if I hit left, oops, I did the numbers wrong. right? We are looking into negative z, and so we're actually looking at. So if I hit up and then left, I'm going to start to rotate in a circle. If I speed up, my circle is going to be bigger. And what's happening here is actually the heading is rotating. As long as I'm holding down the left button, I'm changing the rotation. It's almost like the clock, right? The clock dial is changing. The direction of it's changing. We're going to see how to visualize that in a minute. If I let go of the left key, it'll keep going in the direction that it was going. If I hit slow down, it'll go in the opposite direction. So you can kind of see there's a very complex set of behaviors I can do here. It's quite interesting. And this is kind of annoying. We can't really tell which direction our actual tank is pointing. And so what we want to do is we do want to rotate our thing. And so I will say that we want to rotate our tank to face the correct orientation. So we do need this orientation back if we want to do that. And what's really nice about this is we can actually multiply quaternions by each other. And so now what we can do is we can do orientation is equal to rotation angle times orientation. Now we may get some problems here, which I'll talk about in a little bit. But generally speaking, this is okay. This is mathematically correct. You'll notice now if I hit left and right, my tank is moving. It's going in the direction that it's supposed to go. Sometimes the math will get off, and in that sense, often you'll find that it's better to set a z position, like a z rotation, and then go off of that. So instead of working in the quaternion or working in that math, having kind of a centralized value, because right now both our heading and our orientation are two set of numbers that are kind of representing similar data. And so often what you'd want to do is have a z rotation that we can then manipulate. It's almost like a knob, and then that gets just applied in the update function. But that's not what we'll do yet. It's just kind of a point I wanted to make. So as we're kind of talking about already in the code, you can kind of see that we can apply the velocity to the position, and then we transform it to that position, and we can multiply the direction by the speed to get that velocity. But the next step is, how do we really kind of change this direction, this heading? And that's what we were doing with the quaternions before. Acceleration. So we're kind of already doing acceleration in this example, in a way. You can kind of see how the speed increases or decreases. If I didn't want it to increase or decrease, let me change this to kind of match up with this lecture a bit. I'm going to set it to 1 and 1. And when I don't create that additive thing, we're in this world where we're only going to move. Oops. We're only going to move when the speed is not equal to 0. But we now need to have this else if in here, otherwise. We have to set it to 0, otherwise it'll keep going when we're not meaning for it to. So now if I go up, you can see, right. Sorry. Making a lot of mistakes on this lecture. Sorry. Okay, up, down, right? When I want to go this way, I can go this way. You can see this behavior is a little bit better for this use case, and that it's a vehicle. We're kind of running around. I can back up. I can do all those things that we're kind of used to from video games. Cool. Great. So if you want to think about acceleration, right, in this case, the car doesn't shouldn't stop moving when we stop it, but it should also not go on forever either, like we were doing before. There sort of should be a slow down, right? Like the car speeds up and gets a little bit of acceleration, and should sort of start to slow down. So acceleration is how we accomplish this. Acceleration is a change of velocity, where velocity is a change of position and acceleration is a change of velocity, usually measured in meter over squared seconds squared. And so, it allows us to incrementally add. And so you notice when we added speed, instead of setting a value for speed, we added to it. And so it got incrementally more and incrementally less, and it created that nice sort of momentum feeling. And so when you add this sort of steady rate of increase to velocity on a per frame basis, right, this is kind of what happens. The first frame, our speed is 1. Our next frame, our speed is 2. The frame after that, our speed is 3, and so on and so forth. And so you have this sort of accumulation, and that accumulation allows you to create much more physically feeling motion. Oops. Yeah. So what's kind of frustrating, though, is acceleration does allow you to get to a point where it's too big, right? Like you can go forever and forever, and the speed will get so big that it's, you can't even render it anymore. And so you can use, for example, a clamp, where you can set a maximum value for velocity. You can do this per component as well. Say, your left and your right, your left, like your Y and your Z or X speeds differ for some reason. But generally speaking, you kind of want to probably limit this in your experiences. You don't want things to be able to go as fast as possible. So I'm going to go through the example a little bit more and kind of flesh it out a little bit. But this sort of idea is going to be kind of used almost everywhere, especially in the next unit. We'll really be using this acceleration vector to accumulate multiple forces. For example, imagine shooting a bullet in the air. You got the force of the bullet being shot out of the gun. You've got the force of gravity being pulling it down. You've got negative air resistance kind of slowing it down, and potentially wind that's pushing it to the left or to the right as well. So any given body, right, if you're familiar with classical mechanics, the free body diagram, you can kind of imagine that as a summation of all forces, right? Forces being equivalent to the way that you get your acceleration, where F equals ma, and so your a is going to be equal to all the summation of forces divided by the mass, and that's going to be your acceleration. Then you apply that to get your velocity, then you apply that to get your position. It really is just that classical mechanics equation. And so this is what we'll need. We'll need a bit more of a kind of acceleration, accumulation vector, and we'll talk a little bit about that as well. So, right, we have a velocity, which is going to be the speed times your heading, and then we're going to have an acceleration, which is the acceleration rate times the direction, giving you a new velocity versus your current velocity. It's very similar ideas, right? Like ultimately we're adding vectors to other vectors, and then applying them to another vector, which is your position. So the key is to come up with a rate and multiply the acceleration by the direction, store that in a vector, and then you just do the math. And you want to limit your velocity, and then you draw, and then you set all those positions accordingly. And so I'm going to do this in a minute in the coding, but in the lectures you can see there's an example of how you would do this. This kind of gives you this sort of floaty thing, as we were seeing before. It kind of adds a little bit of momentum and inertia to your object. You can change for a lot of different things to make it feel more natural to you. Like say you're doing something on ice, you're doing it in space, or you're doing it in like dirt, right? It's going to be different parameters that you can kind of play with. Yeah. And one last thing before I go into the code and kind of mess with this a bit more is deceleration. Deceleration is just we already saw this when I was hitting the down, right? The speed was speeding up, and then we're going to speed it down. Acceleration is sort of an opposite force in a direction that often related to your direction of velocity. So if you can imagine drag is usually represented by just a scalar, just a value that you multiply against your velocity. And that's an acceleration. That is a vector that then you use to reduce your velocity. So your velocity in the drag-like environment is velocity minus b times velocity. And in this case, b could be 5%, so you're slowing down 5% every frame, or it could be 95%, where you want to only move. So 95% would be like dirt, right? The car's not going to completely stop when it hits the brakes on dirt, but 5% could be something like being like thrown in the air, or potentially even very, very slippery ice, right? Where it's going to slow down, but very incrementally. And so you can think about deceleration more as like a half-life, in that it never quite goes to zero, right? You're always going to be dividing and dividing and dividing. It's a multiplication minus like less than 1 for the most part. This isn't entirely true, because like you can argue that a deceleration is just an acceleration in the opposite direction of your velocity or your heading. But with that said, you can kind of play with this pretty easily and really kind of get what you want out of it. So here's just an example. The math kind of pops out. You can see it keeps on getting less and less and less and less, but never quite zero. As you can see, almost zero, never quite zero. Why don't we subtract? Well, we don't subtract because if we did, we'd start to go in the negative direction, and that's not really true, right? An object that, imagine being on ice. I play hockey, right? If you take a puck and you hit the puck starts moving and starts to slow down. Eventually it stops. It doesn't start coming back at you, right? And so you do need the multiplication. You don't do this with a subtraction. Is this acceleration physically accurate? It kind of is, but not really. This is simulation. There's a lot more forces in play when you're dealing with the real world. Everything from the air in a room to the like subatomic interactions, like magnetic fields, like there's a million things going on. But is it pretty accurate? Yeah, it's pretty good. It's pretty easy to implement. It's pretty quick to compute, and it gives us much better experiences in gameplay. But it is physically based. This isn't like made up. You'll actually find very often that these equations this math is manipulated in games to create a more game-like experience. This is done often with lighting, for example, where the fall off of lighting is changed to make it more attractive and better lit. But also, I've always played Mario, right? And you hit the jump button and Mario jumps like 20 feet in the air. That's not realistic, right? And also you'll notice that those jumps sometimes are not physically accurate. They don't look like an arc. They're kind of like it's very, so sometimes you do not care about the physical accuracy of movement in interactive media. Oftentimes you just want it to be fun and interactive in media, right? So don't feel bad if what you do isn't perfect. So before I do the coding in this vein of showing how deceleration and acceleration can work, let's talk a bit about the exercise. So this first exercise is per the project, and here is what you got to do, and you need to submit this as an exercise, and hopefully just creating this vehicle, a lot of what I'm doing in this particular lecture. This will be due next week, Tuesday, which will be October. Here we come, Halloween. Awesome. Great, and that's sort of it. Here's some good links as well about the orthographic stuff, because you'll note that you do want, there's portions in this project which we'll talk about. I'm not going to go into it in this coding example, but when the car, or when your vehicle, when your spaceship goes off the side of the screen, right, it kind of goes here and then it comes back here, right? So it needs to kind of clamp using the orthographic projection and understanding how the camera works per the screen size and stuff like that will give you that information, although you can see the line of code here. Okay, so let's go back to our example. Let's position this in 0, 0, 0 just because it's easier to visualize. So what we want, let's kind of understand where we are right now. What we want is we want a movement that doesn't quite stop when we stop hitting the button, and we want it to have sort of a acceleration. And so let's, oops, here we go. And so we're going to go back to our code here, and we're going to create a vector acceleration equals new vector 3. Great. And what we're going to do is now we have an acceleration and a velocity. And when we rotate, what we want to do is when the rotation, we're going to create a rotation angle and get a new heading based on our direction. We're going to set our speed now to be 1. We're going to use this as a, no longer going to use this as an accumulator, we're going to use it as a value, as a magnitude for our acceleration. And now we're going to add to our acceleration the heading times the speed. Or in this case, we're going to subtract it. Oops, no, sorry. No, not yet. This is simply going to rotate us. So this is just going to, this is now manipulating our heading. We're either going left, right, what have you. And now, instead of doing speed, we're going to, instead, acceleration, we're going to add to it our speed times our heading. Or we're going to subtract from that. And we don't need the else if. Like I was saying, you can be pushing both keys up and down and you're kind of creating opposite accelerations there, which is fine. And now to get our velocity is going to be equal to velocity no, not plus. So we have our, yeah, we're just going to add our acceleration to our velocity. And now what's going to happen is we're going to add our velocity to our position. Now the rate of change is when you have the velocity is going to be equal to the every time the acceleration is changing. I see, never mind. It's not a plus equals, we're going to be equals. Or, yeah. So we do have to have the else if here. Sorry about that. And then if not, the acceleration is going to be equal to new vector 3. Yeah, we actually don't need to have a member variable, now that I think about it, because what's the point? And so what's happening here is we have a heading, the heading is changing. And say we don't add any acceleration to the velocity, what you'll see is nothing will happen. I'll just be able to rotate my thing around, but if I go up and down, I'm not going to get anything. If I turn on my acceleration, Now when I hit up, I'm going to give it just a... Oops. I always make that mistake. Let's decrease the speed here, because it's... When you're dealing with accumulation and you're doing like, you hit the key for 5 seconds, like a minute for just a moment, and then you get like 5 frames, and then you have quite a speed up. So now if I hit up, I'm adding a little bit of acceleration. When I hit down, I'm reducing the acceleration. When I change my rotation, I'm still, notice, going in the direction that I was going previously. So if I want to go here, you can notice I have to actually rotate. So this is different than what we had before, where I'm actually creating this sort of like, I have a velocity independent of my acceleration. So when I want to apply a change to my velocity in a different direction, I sort of have to change my heading first and then apply an acceleration. And you can kind of imagine this would be quite useful for a spaceship in space. But this isn't very real for my car. My car should not keep going forever like this. And that's where the deceleration or the slowdown needs to happen. And so here, let's create drag. And the accelerate, in this case, what we need to do is we need to add to the acceleration. Let's create a value here called drag. And let's call it 1 point, let's do 99. Or let's do it, let's make this drag being a percentage. So we have 5% drag. And so what we need to do is we need to have the acceleration apply a negative acceleration in the direction of our velocity. And so what we do is we don't want to make it equal, because then we're going to lose everything above. So we want to add to it. And it's going to be in the direction, the negative direction of our velocity. Right? Like notice if I do this, if my acceleration is always negative, I'll never move anywhere, because I'm always applying the opposite velocity, and I never will actually leave that. And then I need to multiply that by the drag coefficient. Now the drag coefficient here is 5%, and so to make this a little bit more concise, we can just do this. So we're going to apply a negative drag of the velocity, so 5% drag. And in this case, if I go up, I'm going to move down. You notice I slow down. So if I go up and it slows me down, I'm only going to be able to go so fast because it slows me down. This is another way, by the way, to clamp your speed. There's no way for me to exceed the speed, because as I go up, that 5% becomes more and more, and you can probably figure out what that magic number is. There's this what's called the terminal, or the terminal velocity, right? If you've heard this term in terminal velocity, is when I throw a ball out of a window, out of a plane, it's going to hit a certain terminal velocity, which is where the speed up due to gravity is going to equal the slowdown due to drag from air drag, right? And that's you can actually figure out what that velocity may be. So in this case, you can see even 5% is quite aggressive. If I go to do almost all of the motion, my terminal velocity is going to be super, super low, right? So you'll actually find that drags in the less than 10% are usually what are used in games. Sometimes more, depending on it really depends what you're doing, right? There's a sort of relationship between the speed that you choose. Say I do 1, and then I can do 5, like very, very speedy. And you know, it really depends what you're trying to go for here. Like notice also the speed of rotation isn't really the fastest thing in the world, right? I might want to increase my speed of rotation, like 5 degrees per frame, to really speed that up for me. Right? Now I can have that sort of really drift style. Whoa. Can do the whatever. There's a lot of fun things you can do here to create really really fun things, like really kind of diverse control mechanisms. So yeah, I think that's really it. We talked a little bit about clamping, so there is an opportunity here. You can go velocity, I think it's vector 3 clamp magnitude of your velocity. Oops. And then you can say I don't want anything faster than a velocity of 2, or maybe even 1. And this will ensure that you never go above that speed. So notice, I'm never going to go so much faster than before I could go way faster than this. Yeah. And now that's, like you can see, there's a lot of really powerful things that you can do. That's about it. I wanted to share one last little thing. First off, given that this lecture was all about Nicolas Cage, really highly recommend this video, which I'll go out on the credits on. But this is something I wanted to kind of share with you guys. This is a guy on Twitter, Kenny. Highly recommend checking out his stuff. But this is an example with Unity and creating really a unique car controller using like a set of physics rules around using a collider and a ball. So what he's done is effectively he's taken a model of like the car, and inside of this prefab you can see another collider, which is a sphere. And then what he does is he's applying physics to the sphere. So the sphere is rolling, and all the car is doing is really sharing the position of that ball. And then the other thing he's doing is also casting a ray down to see where the floor is of the ground, so to make sure that the car doesn't go through the ground. But that's about it, and you can kind of see how amazing, how physical this really simple idea is, where this little ball is almost like rolling around. You can imagine having just the ball like a marble, and controlling it. When you hit forward, it's applying a force to the ball to roll it forward. And that's really it. This is a very kind of simple set of rules, and it creates a particularly compelling set of behaviors and interactive kind of experiences here. Ones that are probably much more complicated to model if you were going to go down to the physics of the wheels and how these things work. So yeah, games don't have to be physically correct. It's really about making things that are fun. All right, so I think that's it for this week in lectures. But I'm just gonna, go out on this. Anyways, see you guys next week.